So in this video, what I would like you to do is to think about this definite integral, and I'd just like you to explore it with pen and paper, and then after you've thought about it for a bit, if you come back on the next few slides, there will be a detailed discussion of it. So I hope to see you in a few minutes. Okay, welcome back. Let's look at the next slide. So this is the integral that we want to try to calculate. And if we look at the integrand is a square, and therefore the integrand is always going to be greater than or equal to 0. And therefore this integral from -1 to 1 of something which is positive must itself be positive because the integrand is positive. So let's just calculate it completely naively without thinking about what the integral would look like. So here we go. We're going to integrate from -1 to 1 over x squared, which means x to the -2. So you add 1 to the power, so we're going to write down 1 over x, and that's x to the -1. And if you imagine differentiating x to the -1, you will get a minus sign, and then you will reduce the power to x to the -2. So you will get -1 over x squared. We want the integrand, that's plus 1 over x squared. So that's easy. We just put a minus sign in front. And now, if you differentiate this, you will obtain the integrand. And we're going to evaluate this between the lower limit of -1 and the upper limit of 1. So at the upper limit, we have -1 over 1, so -1 divided by 1, so that's just -1. And then we subtract this thing calculated at the lower limit, so I'm going to open a big bracket and then evaluate this at the lower limit. And at the lower limit we have -1 divided by, and x at the lower limit is -1, so it's -1 over -1, and that's plus 1. So we have -1, and that is -2, which is less than 0. So therefore we think to ourselves there is something wrong. Now you might think that we have calculated the integral here incorrectly, but we haven't. You're welcome to check it. So the thing to do is to go back and look at the integrand, the function that we are integrating. So I'm going to sketch the integrand. So it's always going to be greater than or equal to 0, so I can draw the x-axis here towards the bottom. There's not going to be anything below the x-axis. And as x gets larger, this is going to tend to 0 from above because it's positive, so it's going to go that way. And when x is negative, when you square it, you get something positive. And again, as x gets larger and in this direction, it's going to go to 0 from above. And as x approaches 0, and this is the core of the matter, as x approaches 0, this is going to diverge. So let me just try to draw the integrand roughly, and it's going to be something like this. So we see that the y-axis is a vertical asymptote. So the y-axis is a vertical asymptote. And we also see in that way that x is 0 is not an allowed value that you can put into this function 1 over x squared, and we say that x is 0 is not in the domain of f of x is equal to 1 over x squared. So I'll just write down here, this is say where x is -1, this is x is plus 1, symmetrically about it, and here we have our area of integration. So it's going to be something like this. And we start to see that there is a problem that this is diverging. And it might be, and it is, because this is what this inconsistent result is telling us, it might be the case that this integral is not finite and it diverges. And this is what we call an improper integral. So this is an improper integral. Now, sometimes an improper integral converges and sometimes it does not. And this is an example where the integral does not converge. And on the next slide, what I'm going to do is I'm going to show you that it does not converge. So this is just labeling the graph. This is the function that we've tried to integrate. So on the next slide, I will try to be a little bit more rigorous than we were in this naive calculation. So we've said that we are faced here with this integral, which we've said is an improper integral. And an improper integral is one where either there is a divergence of the integrand in the region of integration or where the region of integration is infinite. In this case, we have a finite integration range, but the integrand diverges at x is naught. And the way we can make sense of an improper integral is to use limits. So what we're going to do is, instead of integrating over x is naught, we're going to integrate from -1 to minus b. So b is going to be positive. It's going to be there. Minus b is therefore to the left of the y-axis. And then we're going to integrate from b to 1. And again, b is positive, and this is to the right of the y-axis. So our integrand can clearly be just broken up into the integral from here to 0 and then from 0 to the upper limit. But then around 0 we use limits to calculate it, to make it finite. So we calculate finite integrals and then we take limits and see what happens as b goes to 0. And the way I've defined it in both cases, b is going to 0 from above. It's positive. Note, by the way, I could have used a different symbol here to the one I use here. I'm just doing this for simplicity. Okay, so we just calculate the integrals. So it's going to be the limit as b goes to 0 from above, so it's small and positive. And the integral of 1 over x squared, we said a moment ago, is -1 over x. You can verify that if you don't remember it. And that is from -1 to minus b. And similarly here, it is plus the limit b goes to 0 from above. And the integral of 1 over x squared is -1 over x. And that is from b to 1. So we can now start to evaluate this. So let's say that we have the limit as b goes to 0 from above. And at the upper limit here, we're going to have -1 divided by minus b. So that's going to give us +1 over b. So that's +1 over b minus, and then at the lower limit, I'm going to open a bracket to be careful because we might make a minus sign error otherwise. We are going to have -1 over x, where x is -1, so it's -1 over -1, so it's +1. So in the brackets here, it's 1. And that is our result. We've still got to take the limit for this term here. Now, just coming back to the integral, this and this look very much the same, and in fact they are the same, because 1 over x squared is the same whether you have positive x or negative x. 1 over x squared we say is an even function. So this result here for this part of our integral and the result for this are going to be exactly the same by symmetry. And I'm not therefore going to go through this. You can do it yourselves. You'll see that you get the numbers swapped around a little, but you are going to get exactly the same result. So you're going to get plus the limit as b goes to 0 from above of, and now it's going to be minus 1 plus 1 over b from the lower limit. And you're very welcome to go through that and check it. So if we look at these terms, they're identical. So let's just focus on one of them. It's just going to be multiplied by a factor of 2 overall. Now, b is positive because we are here keeping to the left of the y-axis and here to the right of the y-axis. So b is positive, minus b is negative. And b, you know, is less than 1. So 1 divided by b is bigger than 1. So overall, for any b less than 1, this is going to be positive, as we would expect because our integrand is positive. And also, as b approaches 0, this is going to diverge. So what we see is that our integral from minus 1 to 1 of 1 over x squared with respect to x is going to diverge. And we say that the integral does not exist. There is no finite value for this integral. And what's happening here is that as you make b smaller, or as x approaches 0, this integrand is diverging, and this is diverging sufficiently rapidly that the area between this curve and the x-axis here is divergent. Now, it is possible for such an integral to diverge in such a way that it diverges slowly enough for the area to be finite and for the integral to exist. And I'm going to give you an example of that to look at on the next slide. But we call integrals like this one, where the integrand is diverging over our range of integration, we call them improper integrals. And what we've done here by introducing these cutoffs is we've made them into proper integrals, and by using the limiting procedure we've been able to verify in this case that our integral did not exist. But sometimes they can exist, and that we're going to see on the next slide. So here is the integral that I suggest you conclude this video with. Calculate this integral both naively and also using the limiting procedure, and you'll see that you get the same answer, because although this integrand diverges, it gives you a finite result for the integral. And what I would suggest you do is that you just pause the video, come back in a moment after you've tried it. Okay, welcome back. Let's have a look at the integral. And I'm going to start off by sketching the integrand. So the integrand, 1 over root x, what does it look like? Well, it's only going to be defined for x positive because we have the square root here of it. So x has to be positive for this to be real. And the square root of x is by definition positive if x is real. So we have 1 divided by something positive, the integrand is positive. And it's going to look something like the following. So it looks naively something like what we had a moment ago, but the devil is in the detail and you can't necessarily easily see the difference by eye. So we're going to integrate up to x is 1, and this is an improper integral because as x approaches 0, we are dividing by the square root of 0, so it's going to be approaching 1 over 0. So this is an improper integral, and the integral corresponds to this area here. And to make sense of it, what I'm going to do is I'm going to say that we are going to integrate from a minimum value that I'm going to call b, and that means that our integral is now defined as being this area. It's above the x-axis, so the integral does correspond to this area. So what we say is that our integral is equal to the following. The integral from 0 to 1 over root x dx is defined as the limit as b approaches 0, so taking our cutoff here b and making it smaller and smaller, so taking this dotted red line towards the y-axis, so it's approaching 0 and it is approaching 0 from above. It's staying positive. And it's the integral from b to 1 of 1 over root x dx. So this is the limit as b goes to 0 from above of. Now, this integrand is x to the minus a half. Add 1 to it, you get x to the half. So I'm just going to write x to the half, or equivalently, I could have written the square root of x, but I'll call it x to the half. Now, if I differentiate that, I would obtain a half in front times x to the minus a half, so 1 over root x. And the 1 over root x is good, but I don't want the half in front, so what I do is I put a factor of 2 in front of it. And this is evaluated between the lower limit b and the upper limit 1. So this is now the limit as b goes to 0 from above of 2 times the square root of 1, which is 2. That's the upper limit when x is 1, minus, and then it is 2 times the square root of b. That's the lower limit. Now, as b goes to 0 from above, this stays as 2, but the square root of b, since b is positive, it's defined, but as b gets smaller and smaller, the square root gets smaller and smaller, and it approaches 0. So in the limit, it's approaching 0. So this tells us that our result for the integral from 0 to 1 over root x dx is equal to 2. And that is a finite result. And it is also positive, which is what we would expect from looking at the integrand. So I'll just make that comment, positive as expected. So at the risk of showing my age, let me just tell you something that I remember about improper integrals. There was an old song many years ago called "You Can't Put Your Arms Around a Memory," and you also can't put your arms, or a line like this, around an improper integral. By introducing this cutoff, we've made it into a proper integral. But an improper integral, either if you integrate out all the way to infinity, you can't put a finite line all around it. Or if the integrand diverges upwards or downwards, you can't put a circle or a shape all around it. So you can't put your arms around an improper integral, and maybe that helps you to remember what sort of things they can be. And with that, I'll stop this video.